Okay, thanks for the introduction. My name is Sigal. I'm from the University of Bristol. And today I'm going to talk about power analysis on ARM M0 processors. So first thing first, what is side channel analysis? I guess many of you are probably already familiar with this concept, extremely after this year's meltdown spectre drama. So loosely speaking, any attack that based on information leakage, such as operation time, power consumption, electrical magnetic radiation, can be regarded as a side channel attack. As we can see in this figure, so in a side channel attack, the attacker not only controls the encryption-decryption interface, but also captures the information leakage during the encryption process. It turns out such information leakage can be extremely dangerous. In certain circumstances, the attacker can learn the secret key within a few minutes. So due to its clear leakage and wide deployment, ARM processors are indeed quite popular in side channel research. In previous attempts, we have timing attacks like with the unbalanced branches or branch predictions. We also have cache timing attacks, also some early termination problem in the multiplication instruction. And we also have power analysis, whether it's simple power analysis or differential power analysis, also EM analysis on both the high-end processors and low-end processors. So to mitigate the threat of side channel analysis, the common solution would be adding countermeasures into our implementation code. However, this is by no means a very trivial task because we can simply make some mistakes which will ruin the whole security. So it is definitely desirable for us to have some early detection tools to tell us where we go wrong. In terms of power analysis, this means we need some power simulators which will provide you simulated traces without an actual running encryption device or a very expensive oscilloscope. You can do this simulation in various levels. For instance, you can do it in a circuit level with tools like HSpice or Xtime, taking the gate level netlist and a few maybe more details on the low-level circuit into consideration. You can have a very accurate simulation. On the other hand, this kind of simulation can be really slow. In terms of like state-of-the-art leakage detection techniques, we usually takes like at least 1 million traces. So this kind of simulation might be way too slow for that. You can also do everything in a higher level with C code or even like Python code. But the problem with that is like you didn't even take the compelling effects into consideration. So the simulation becomes quite not accurate. You can also do it with binary code with the help of some instruction simulators. The question now is what kind of model assumption you're going to use. Are we going to be satisfied with the generic Hamming weight or Hamming distance model? Is it enough to just use this generic assumption? Or like many other, previous side channel researchers sometimes use this user-defined model. I guess this is one of the options many cryptographers really love because, it seems to me like sometimes we just, if there are anything wrong, we're just blaming the implementation. It's kind of weird, like sometimes we didn't even know how to do it right. We're just blaming the engineers for doing it wrong. And of course, I'm not going to be one of those cryptographers here, so there's a third way, which is learning the power model from real-life acquisitions. To this end, let me introduce our model, to ELMO. So ELMO is our emulator for power leakage for the ARM M0. It has an embedded emulator inside, so it will simulate what's happening inside this ARM core. We have a profiling power model, which is carefully derived from a real ARM M0 core. Given the binary code, ELMO can produce the simulation traces together with some state-of-the-art fixed versus random leakage detection test. So I won't really go to details about the fixed versus random t-test. Let's just say if the Ttest here have some value higher or lower than certain threshold, here is 4.5 or lower than minus 4.5, we say this sample has some exploitable leakage. And you would like, for countermeasures, you would like to cover this up. So as we can see, the Ttest results here, what ELMO produced is quite similar to what we observed in real traces. So the leaky cycles are quite similar. And another interesting property of ELMO is it provides exactly one sample per cycle. So we can quickly link the leaky sample to the leaky cycle to the corresponding assembly code, which will help the crypto engineer locate and fix the specific issues. Okay, so by far, this is what we published last year in Usenix, and also have a presentation here. So what's new this year? Well, if you think about it, one of the biggest problem for profiling model is that its coverage becomes quite questionable. So we got our model from one specific ARM core, which is M32. Does it work on all the other ARM M0 core, especially considering like for ARM, the M0 have manufacturers all around the world, and we know for sure that the power consumption or power leakage is strongly depends on specific implementation. So leakage-wise, do we have some manufacturer-specific features? Does the electrical components on the board affects the leakage? Or in summary, can we use the same power model for all the ARM M0 cores? So to study this, we have to use some new ARM M0 core, possibly from another manufacturers or even with another board. So I will skip this and the next slides, but what you need to know is here we build a new board with a new core. Here is the NSP LPC1114, and we'll also have very stable power consumption measure point. If you're interested in this board, it's open source now, so if you're interested, you can talk to me afterwards. So for the following of this talk, I'm gonna use this board as our target. So the first thing I do is replicate what happens in our previous experiments in ELMO. So we tested 23 basic farm instructions with the move instruction move triplets with all the operands using random numbers. So in our leakage analysis, we consider both the operand and the bus transition, which is much more accurate than the generic assumption like Hamming weight or Hamming distance model. And our regression results is as this. So here, all the gray box stands for this factor doesn't really matter in the leakage. And what you need to look at is the red box. Here is the difference between the old board and the new board. So there are very few differences, and most difference lies in the first operand, whether it's the first operand in shifting instructions or here with the store instructions. But besides that, all other factors are quite similar. And we further cluster these 23 instructions according to their leakage. All of the clustering results is quite consistent with our intuition, which is all the ALU instructions have rather similar leakage, so they fall into the same cluster, whereas the store and load instructions have a separate standalone cluster. And the only difference with this two board here is with the ST board, the shift instructions, it stands alone as a separate cluster, whereas for this PC board, this new board, the shift instructions will oh, sorry. I think here I make mistakes. It should be this. The shift should be a separate cluster in the SD board, not in the new board. In the new board, it's just merged with the ALU instructions. But so far, we have talked about the similarities. But if you take a closer look at the bitwise leakage, there are some significant differences. Specifically, let's look at the multiplication instructions. So here, the blue line stands for the leakage for the first operand, and the red line is the second operand. So the left, we have the old board, and the right, we have the new board. We can see here, it seems like the rows of the first and second operand has been exchanged. What does this mean? Well, we're still investigating on it. We are suspecting like this has something to do with the specific architecture. It might be like which operand goes to which bus causes such difference. But right now, we don't really have very solid evidence. OK, so our conclusion here should be the power model of LPC1114 is quite similar to what we observed in ELMO, which is STM32. This suggests our security evaluation with ELMO may be still reasonable, at least in theory. And we also observed some structural difference, like the first operand and second operand in the multiplication of instructions. What this means in security, whether it does affect the leakage, but whether this leakage can be explored, that still takes time to confirm. In the meantime, I also have noticed some very interesting features. So during our experiments, we constantly find out the leakage for different instructions won't really lie on the same location on the trace. As we can see here, the left figure is an AND instruction, and the right is an OR instruction. So it seems like for the leakage of the OR instructions has been delayed for a while. And we further find out this has something to do with the specific code layout. So as we can see here, in this table, the left column and the right column has exactly the same code. So nothing changes here. But the system tick, the CPU counter, suggests the left one takes 5 cycles and the right one takes 7 cycles. So we suspect this has something to do with the instruction prefetch. So the red line here lies in a specific position where a new instruction line needs to be fetched from flash to RAM, which takes 2 actual cycles. What does this mean for security? Oh, sorry. So to verify our speculation here, we try to run this code from RAM. So if it's run from RAM as expected, it always takes 5 cycles, regardless of the specific code layout. What does this mean for security? Well, the direct consequence will be for branches, even if it's perfectly balanced, considering their code layout might be different, they might still have different operation time. This means as the code layout depends on specific compiler, balancing branches will become much more difficult. In the meantime, we can also see this instruction prefetch on the raw power trace. So here we have one figure from the oscilloscope. So you can see each peak here actually stands for one instruction prefetch. For this core, it has a prefetch every 8 instructions, and the prefetch itself will last for 2 cycles, so altogether 10 cycles. If you count the time, it's exactly what happens here. And from here, we can have a very clear roadmap of what's happening inside the core of the CPU execution. So what difference from this attack, what difference this attack have with all the previous attacks is that here we don't really need a high-end, very expensive oscilloscope. You can use very cheap device. You might still observe the same phenomenon. So this could be possibly useful for other attacks in the future. As for the future plan, we are planning to support more, processor series, like the M0 Plus or M3. We are also interested to learn the model quality. In theory, our model is much better than the Hamming weight or Hamming distance model, but we don't really have a metric to measure how much benefits we got from this profiling model. And also, as stated before, we would also like to learn whether different setup affects the leakage. Okay, so this project is supported by the European Union Horizon 2020 Reassure project. This is the end of my talk. Thanks for your listening.
Thank you very much. Are there any questions for the speaker at this point? No? In this case, I have a question.
Yeah.
So do you see any potential to feed your model into a security-aware compiler so that it might be automated to avoid certain instruction sequences that could leak information?
Well, for Z channel countermeasures, right now we don't really, it's not like a certain instruction sequence might leak information. It's any instructions that operating on the secret intermediate state, so the secret key related data will leak information. So basically most common what we do is like, well, whether you do some shares, data shares, you share the secret data with a few random numbers. So it won't be like one data, one intermediate state leaks all the information. That's what we usually do, rather than just some instruction sequence might leak the information, because all the instruction, basically all the instruction triplets will leak information.
Sad to hear. Okay. There's a question in there.
Yeah, maybe following along from what you're asking
Yeah.
about compilers. So right now you looked at essentially just low level, like an OR or an AND instruction.
Yeah.
Is there, so probably to get something meaningful from a security perspective,
Yeah.
for instance, to figure out when you're processing keys or something like that,
Mm-hmm.
you need to move up move up to more like the level of sequence of instructions. Is there a way to automate that? Because that would be a very tedious process. Are you planning to look at kind of looking at the profile or the sequencing of instructions?
Well, I didn't really get like what you mean by automate.
So just looking at an individual or and
Well, for ELMO, actually now this is an automation tool. You can just give them the binary code.
okay.
Then ELMO will produce you the traces. What we do here is comparing the power model. We have also produced a new, new coefficient file in the new power model for this new board. But what we see here is it doesn't really have a significant difference from the old board. So probably we can still use the old power model and still use the ELMO in the original form we published last year. So it might still work. So it itself is an automation tool. It's not like that. It doesn't really take things like you manually write it as like AND instruction or instructions and then do the simulation. You don't really have to do that. The tool itself will do everything.
Okay. So I'm just thinking that to make this more powerful,
Yeah.
eventually you want to be looking at, for instance, when you start to do secure boot, looking at standard code for secure boot, and
Yeah.
that's where you could actually have a vulnerability, not on individual instructions.
Yeah. Well, for your question, if you have like secure boot, you have one secret in the probably in the flash or in somewhere stored. Then you can just compile that secure boot into a binary code, and then you give it to ELMO. The current workflow is like this, and ELMO will produce your simulation trace. And also with fixed versus random test, so if you see something here like higher than the threshold, that's a problem. Yeah, that's probably a leakage, and you will see like what happens there, whether I should fix it.
Okay, great. Thank you.
Any more questions? Okay, with that, please thank the speaker again.